There, it's starting to record. Now, if you loosen that, it'll lean back.
Loosen this?
Yeah, see? And then you can tighten it again. See what I'm saying?
Good.
Got feel?
Got it.
Alright, this is helium because it has 2 protons. What do we call it if it has 1 proton? Hydrogen. What do we call it if it has 3 protons? Lithium. What do we call it if it has 4 protons? And so forth. And the most important to us, what do we call it if it has 6 protons?
Carbon.
That's carbon. And that's probably the most important biological molecule because it can bond to 4 different things because it has 4 electrons in its outer level.
Can't nitrogen also form long chains like carbon?
Not as well as carbon,
Okay.
but it could. It can bond to 3 things.
I'm hearing something that is like it's possible that life somewhere else is all like nitrogen based, right?
Silicon probably, which because silicon can bond to 4 things also.
Okay.
The silicon bonds are a little weaker, so it'd probably have to be a cooler planet. There's a whole Star Trek episode on this.
What?
Okay, so protons are positively charged, neutrons are neutral. Did you know neutrons are like glue? They hold the protons together in the nucleus. See, the protons are both positively charged. Opposite charges repel one another. So wouldn't you expect the protons that are touching one another to fly apart? They're glued together by neutrons. That's the purpose of neutrons.
What?
There's only one atom without any neutrons. You know what it is?
Hydrogen.
Hydrogen. It's just a single proton in the nucleus. This is good stuff, isn't it? Are y'all excited about atoms?
Yes.
Often you'll see an atom, the symbol, with 2 numbers next to it. The smaller number is called the atomic number. That's the number of protons. Excuse me. Carbon has 6 protons. The bottom number is the mass number, or the larger number is the mass number. That's the number of protons and neutrons combined. So carbon-12 has 6 protons and 6 neutrons to make 12 total particles in the nucleus. So that gives it a mass number of 12. What's the difference between carbon-12 and carbon-13?
1 neutron.
Carbon-13 has an extra neutron. Was that you, Dylan, said that?
Yes. Does it mean 3 bonus points?
No. Happy points.
I'm always happy.
Greta, can you slide over just a little so you're more 6-footish? Thank you. Got to make sure to stay separate. They'll come in and check. I'll get in trouble if y'all are close together. You see what I'm saying? It's all about me. Okay. Hey, here's a guy finding fossils. You can carbon date fossils. Do y'all know how carbon dating works? These we call carbon-13 and carbon-12 isotopes. Isotopes have different numbers of neutrons in the nucleus. Isotopes are often radioactive. There's a radioactive isotope of carbon called carbon-14. It makes up about 1% of your molecules, of your carbon atoms in your body. Did you know that? 1% of your carbon atoms are radioactive? Isn't that cool? You're radioactive.
Yeah, it is radioactive.
And if you die and your bones are somewhere, that radioactive carbon is still in your bones. And the carbon-14 that's in your bones will gradually decay and become nitrogen and stop being radioactive. And so they can tell how old bones are by how much radiation there's left in the bones. Yes. It's called carbon dating.
But with fossils, doesn't it, the material from the bone isn't there. It's been replaced by other sediment and minerals, right?
In really old fossils.
So how do
But carbon dating only works back about 50,000 years.
Okay.
So it takes longer than that to form an actual stone fossil. Those are millions of years old.
Okay.
Now, if they want to radioactively date stone fossils, they don't use carbon dating. They use uranium dating, or I think there's thorium dating or something else, which are other molecules that are in the stone that also decay.
Okay.
So it's done a similar way, it's just with different elements. Make sense? Dylan, I like your questions, sir.
Thank you.
Anybody has any questions, don't feel free to ask. So over about 50,000 years, you can't use carbon dating. But it works well for anything under 50,000 years, like if you found a mammoth skeleton or something. You know when the mammoths went extinct? Yeah, about 10,000 years ago. So if you find a mammoth skeleton, it's probably less than 50,000 years old, and you can figure it out. All the elements are ordered in the periodic table, in a certain way. Y'all should have learned this in chemistry. The first row all have one valence electron. The first column. The second column all have two valence electrons. This column over here has 3. This has 4. This has 5, 6, 7. And all of these have 8 valence electrons. Do you guys remember that from chemistry?
Yeah.
These are called the noble gases. So, the number of electrons, of course, depends on the number of protons. If an atom has 10 protons, it's probably going to have 10 electrons. And they neutralize each other so to make the atom neutral overall. However, atoms can gain and lose electrons. And that has to do with bonding between atoms. So that's what we're going to get into next. Are we still in 2.1?
Yeah.
Still got a long ways to go?
Yeah.
This is the Bohr model of the atom. This is the first energy level, the second energy level, the third energy level. Electrons exist in energy levels. The first level can hold 2 electrons. The second level can hold 8 electrons. Does anyone know what the third level can hold?
30.
18. Do it, Thomas.
Yeah, Thomas.
Now, even though the third level can hold 18 electrons, it's stable when it's holding 8. When it has a full 8 in the third level, that's stability.
Wait, but what if it's holding like 12? Is it not stable then?
Well, it can be. That's a chemistry thing.
Oh, okay.
You know, do you remember that they go in 4s before they go in 3d? You know, that kind of thing?
Mm-hmm.
So you want a full outer level.
Mm-hmm.
So if 4s is full, then they can start going in 3d, and that's okay.
Okay.
You see what I'm saying?
Yeah.
But that's really beyond the scope of the biology class. So I'm not going to talk about that much. But they want a full outer level. So every atom in group 1 and in group 2, they don't have full outer levels. Only the noble gases have full outer levels as individual atoms. But what you're going to see is atoms come together to share electrons to make full outer levels. Do you remember that from chemistry? Did y'all study the shapes of the orbitals?
Yeah.
S orbitals are round. P orbitals are shaped like figure 8s. D orbitals have this weird shape. We're not going to get into that much. The book talks about it a little bit, but this area is kind of is what we call the electron cloud. It's where the electrons in orbital like to hang out, and the electrons are moving so fast it kind of just makes a blur, and we call that the electron cloud. And you can never know exactly where the electron is in the electron cloud. It's somewhere in there, but there's no way to figure out exactly where it is. We call that quantum effects. Have you ever heard of quantum physics?
Mm-hmm.
Ooh, it gets out there, man. It's also beyond the scope of biology. So you can look at these orbitals and read about them, but you're not going to get many questions about shapes of orbitals. It's chemistry stuff. We go through the introductory chemistry to get to the biology. Now, you could have that on a quiz, maybe a bonus question or something, but it's not one of the major ideas here. But bonding is important. This shows how hydrogen bonds to oxygen. And I have some magnets here, and you may want to get the camera on this over here. I have some magnets, and we're going to be using a lot of magnets in this class. And these are my magnets that represent water. This is my water magnet. Water consists of oxygen bonded to two hydrogens. Can you tell that's H2O? You're going to be, one of the things you're going to be doing, why I've had extra whiteboards put in, is your group is going to be manipulating magnets on the boards and making some of this stuff happen. So pay good attention when I'm using magnets up here, okay? Because you're going to have to do it too. But these magnets, so a water molecule is two hydrogens bound to an oxygen. These are electrons. They represent the electrons that are shared between oxygen and hydrogen. Do you remember that covalent bonds form between oxygen and hydrogen to make the water molecule? They're sharing electrons. I'm going to put those shared electrons right here. So that's the shared electrons between the oxygen and the hydrogen. I'm going to put another one there. And now we've got that bond. Those electrons shared between oxygen and hydrogen make the oxygen have a full outer level, and it makes the hydrogen have a full outer level. Here it shows that. See, oxygen has 6 electrons in its outer level. It wants 8. Hydrogen has 1 electron in its outer level. It wants 2. Hey, if we all hang out together, we'll all be stable. The hydrogen shares 1 with the oxygen shares with 2 different hydrogens, and now the oxygen has 8 and the hydrogen has 2. Everybody's stable. It's going to be hard to pull that molecule apart because all those atoms are so stable. That's what a covalent bond is. It's sharing electrons.
Isn't the hydrogen sharing 2?
Each hydrogen is sharing 1. So this hydrogen is sharing that one with the oxygen, and this hydrogen is sharing that one with the oxygen.
And the oxygen sharing the red one?
The oxygen is sharing the red ones with the hydrogens. Does that make sense? Now, you know, if you were to draw this molecule on the board, you would draw it like this. You would draw the oxygen and you would draw dashes to represent the shared electrons. Each dash is shared electrons, and we call that a covalent bond. Have you ever heard of that before? A covalent bond. It's just like if me and Thomas were going to share this marker. Let's grab that end of it. There we go. We're bonded together now. You can't tear us apart, especially if we're happier with the marker. Are you happy? We're both happy. You're not going to get us apart. We're going to be walking around all day with this stuff. Okay, you might go. We don't want to like it. I'm oxygen. I'm hogging the electrons. Did you know that it's not equal sharing in a water molecule? It's unequal sharing. The oxygen tends to hog the electrons. The shared electrons stay closer to the oxygen than they do to the hydrogen. That makes water what we call a polar molecule. Polar means charged. And the oxygen will actually have a slight negative charge, and the hydrogens will have a slight positive charge because of the unequal sharing of the electrons. And that's a very important point. It gives water a whole lot of weird properties that help us live.
Is that why ice floats?
That's why ice floats. It's why there's surface tension on water. It's why water falls in drops. It's why it runs up tubes, sticks to the board and to glass and to cells. There's all sorts of neat things about water. Now, oxygen could share 2 pairs of electrons with another oxygen. And we call that a double bond. And that's a very important molecule for our studies. It's O2. Have you heard of O2 before?
Yes.
That's what you need to breathe to survive.
Why is O2 like good, but like O3, that's
O3 is ozone.
right, that's not good.
Yeah, if molecules bond different ways, they have completely different properties. And what ozone does is it's bad when it's close to the ground. It's pollution that comes out of cars. It's good if it's high up in the atmosphere. It absorbs the harmful ultraviolet rays from the sun. And what we found out was a chemical we make called chlorofluorocarbons tears up the ozone up in the atmosphere.
Wasn't that in like refrigerators?
It was in refrigerators.
Plus,
It was in spray cans. It was in air conditioners and transformers. We used it for a lot of things. We didn't realize it was floating up there, tearing up the atmosphere, until a couple scientists started studying it and they realized it. And then we phased out those chemicals and we don't use them anymore. Those 2 scientists are credited with saving the Earth. Wow, it's pretty cool, isn't it? What did you do in your life? I saved the planet. Me and this other guy. I saved every living thing on the planet. The planet would have still been around, but all the life would have been gone. That's a pretty good accomplishment, I think. Saving every living thing on the planet. Oh, let me tell you about ionic bonds. Do you remember about ionic bonds?
Yes.
Ionic bond is when you don't share electrons. It's when you give electrons. Imagine that this is a negatively charged object, an electron. If I give it to Thomas completely and I'm done with it, he has just taken an electron, right? He becomes negatively charged because he's got an extra electron. I become positively charged because I gave away something that was negative. If I'm positively charged and he's negatively charged, we're going to stick together like magnets. So that's an ionic bond. We can't do it because you got to be socially distant. But see, the Na, to get a full outer level, it wants to get rid of an electron. The Cl, to get a full outer level, it wants another electron. So it's a good proposition for both atoms. This gets rid of one, this receives one, but now they're stuck together like magnets. That's an ionic bond because they become charged. See, Na becomes plus, Cl becomes minus. They're both charged. Now they'll stick together like magnets. They each have different numbers of electrons than they used to have. Salt is very important. Doesn't salt taste good? Don't you like salty stuff? That's because your body has evolved to like the taste of salt because you need sodium to run your muscles and nerves, and you need chlorine to help move things through cell membranes. Those are important ions. You need them in your diet. So you have evolved liking the taste of it, so you'll eat it when you come into contact with it.
Do you think we would like it?
There are some things that don't need it and they don't like it.
So why don't we evolve to like broccoli?
Because you don't really need it. It doesn't supply much calories.
I like
Because it's a
broccoli.
plant. It's mostly cellulose. Now, it does help clean your system out. But it doesn't taste that great because it's not supplying you with energy. But I kind of like broccoli.
I like broccoli.
But I usually put salt on it, so maybe that's wrong.
Double healthy.
So, this is talking about molecules being polar or nonpolar. Here's a water molecule. It's a polar molecule because of the uneven sharing of electrons. Here is a methane molecule. It's nonpolar because it evenly shares the electrons. There's no one part of the molecule that has the electrons closer to it than the other. So that's basically the difference between polar and nonpolar. Often it has to do with the shape of the molecule. If it's a straight molecule, like carbon dioxide, it's going to be nonpolar. If it's a bent molecule, like water, it's usually polar. So, a hair straightener is being used on a girl's long, dark hair. Okay? Just, random things to say. What they're talking about is denaturing. Do you remember what this is? I held it up about 1,000 times in biology. When you said amino acids. It's a chain of amino acids, and it usually will fold up into a certain shape. And that's a protein. Now, the reason why it folds into a shape is because of attractions between charged R groups. I don't know if you remember, but each amino acid has an R group. And so if that's a positive R group and that's a negative R group, they'll attract one another and kind of touch one another. And so that makes this thing fold into a certain shape based on the attractions. Well, if you heat up a protein, anytime you heat something up, it just starts moving faster and it'll just come apart. I always enjoy doing that. You want to see it again?
Yes, please.
It folds up into its nice shape, and it'll stay that shape until you heat it up. And then it starts vibrating faster, and it comes apart. That's denaturing. And that's what happens when you use a curling iron. You can denature it, change the shape of the proteins, and make them take whatever shape you want. You can wrap them around the curling iron, let it cool, and it'll curl.
It's okay.
Isn't that cool?
Let's go.
Let's go.
Oil and water don't mix. That's because water is charged and gets attracted to other water molecules. These water molecules will stick together because there's a bond between them. They're called hydrogen bonds. The positive hydrogen is attracted to the negative oxygen. They'll come together and attach. But if you have oil is an uncharged molecule. It's not attracted to the water.
I think this is 2.2.
That's why oil and water don't mix.
I think it's 2.2.
I went to 2.2? Y'all stopped me at the right time. All right. Thank you for watching. Mr. Willis